So 2.4 powers, which are also called exponents, and then we'll talk a little bit about square roots as well. But we're gonna compare the square roots with the multiplication table. Really, the exponents are gonna be multiplication table stuff as well. But there's a little bit of extra vocabulary that we need in exponents. So this is the vocabulary we need right here. We got a base, and we also have an exponent, which again you could also call a power. So you kind of notice that the 4 here is a little bit smaller. The smaller of the two is always the exponent, and it needs to be in the top right. If it's in the bottom right, it means something different. So don't put it in the bottom right, okay? But this is the format for exponents. And yeah, we could say, well, you could do it abstractly like this. Sometimes they will. That'd be a to the power of b. But just to understand, like if you saw something like this, there's a few ways to say. You could say 5 to the power of 4, 5 with an exponent of 4. The most common way is this, though. This would be 5 to the power of 4, though, okay? But 5 is the base and 4 is the exponent. You have to know those two vocabulary words, because if we see exponents in the future in this class, you need to understand, okay, if I call it a base, then you know that we're talking about this number here. If I say the exponent, then you know we're talking about this number here. Now, what do exponents do? Well, exponents is just really simplified multiplication, right? So we've seen that addition can be simplified if it's repeated into multiplication. Well, math people found that, because they like to make things more complicated, that if you start having to multiply the same value over and over and over, well, they found a way to simplify that, and that's where exponents come in. So the base, as you can see here, like 6, that's the number that's being multiplied by itself. Okay, and then the exponent tells us how many times. So 6 to the power of 4 is 6, but multiplied by itself 4 times, right? 1, 2, 3, 4 6s. Or 7 to the power of 5. So it's 7 being multiplied by itself 5 times. 1, 2, 3, 4, 5. 5 times. Okay. Now, I don't think that we'll see any calculations of to the power of 5 or even to the power of 4 in this homework. But probably some powers of 2. But as long as you can write these out with repeated multiplication, then really that's all you need to focus on, because, well, I mean, that's kind of the point of this unit, is some multiplication, some division. So right here where it says simplify, let's go ahead and expand this out just so we can understand what it is telling us to do, right? We got a 5 base with an exponent of 2. So it's really 5 multiplied by itself, well, 2 times. So it's really 5 times 5, right? We got 2 5s there. And this is one of our multiplication facts that we should have down. This is 25. So 5 to the power of 2 is 25. And again, this goes back to sometimes math, it shows the same thing but in different ways. This is one of those ways, right? You could say 25, is 5 times 5. Or you could say, well, 25 is 5 to the power of 2. It's the same thing. Oh, this one, I didn't expect to see a power of 3 on this. That's okay. We can still do it. Again, this is 8 multiplied by itself. We got 3 8s. 8 times 8 times 8, okay? Now, I would focus just on the first 2 here. I mean, unless you can do all that in your head, that's fine as well. So I would start with the first 8s. The first 2 8s, that's 8 times 8, right? And again, this is one of our multiplication facts. That's 64. But then to multiply this last 8 right here, I would probably need to show some work. So 8 times 4 is 32, so I carry the 3. 8 times 6 is 48, but then plus the 3 there makes that 51. Okay, so you, well, I guess you could have expanded that if you'd like, but whether you need to or not, you should still get the same answer of 512 here. Okay, so that's our product here. And again, yeah, it is an exponent, which is just repeated multiplication, so it is a product. So 1 to the power of 5. This is 1 multiplied by itself 5 times, right? So 1, 2, 3, 4, 5. Now, sometimes students will look at 1 to any power, right? We could have made this 592, like it's something gigantic. But when the base is 1, just remember anything times 1 is itself. So even if you took this 1 and multiplied it by 1 a million times, well, the result there It's just 1. That's our product. So I did kind of take a shortcut on that last one. I hope that's okay. But again, when multiplying by 1, if you just multiply 1 by itself, it doesn't matter how many times, it's still going to come back as 1. So yeah, here we go. We got these ones. We need to write these in exponential form. So remember, you got a base, and then you got an exponent. It's just kind of a smaller number here in the top right. So the base is the number that's being multiplied over and over and over. In this case, it's 2. So that's my base. And then the exponent tells us how many times it was multiplied by itself. And that's 1, 2, 3 2s. So this is 2 to the power of 3. Just clean this up a little bit. There we go. 2 to the power of 3. And when you get to the homework, what's going to happen is when you click on the box, you'll see a box open below it. And then I think it shows like a box and another box. If you want to access the exponent button, it's really just Shift 6 on your computer. And if you look at the 6, you're going to see somewhere on the key this little symbol right here. That's the exponent symbol on computers and calculators, by the way. So later on in later classes, when you are able to work with exponents in calculators, you'd be looking for this button on your calculator. But this is how you would type it in. If you don't want to use that, it's called Math Quill on there. So a problem like this one, when it wants exponential form, it means that, right, we got 8 times 8 and 5 times 5 times 5. That's 2 different bases, and yeah, we can work with those. So I have a base 8 and also a base 5, all right? So let's start with the 8. The exponent, how many 8s are there? There's 2, so that's my exponent. The 5, how many 5s are there? 1, 2, 3. So my exponent is 3. And this is really all they want. You can type in the multiplication in between. That would be fine. Again, that's just the asterisk button on the computer. All right, square roots. To find a square root, it's the same thing as trying to find the length of a square, or the side length of a square, if you were given the area. Well, why is that important? It's because squares, which is why it's called a square root, squares are unique because the side lengths are the same, right? So each of those side lengths, I put S's there. Those are S's, not 5s. S for side length. But to find side length the area of a square, you'd say, well, it's side length times side length. And I know some of you guys wanted me to put, I forgot to pull up the screen. Sometimes students want me to put S times S. I'm just not going to do it. Hopefully the reasons are obvious. But I'm not going to do it. So area side length to the power of 2. Side length times side length. Well, that would be fine if you had the side length. But if you don't have the side length, you just kind of have to think about this. What number, right? Because that's really what we're asking. Something times itself, that's the area. Okay, so what number times itself would be whatever the area is that they give us. So if you saw something like this one, it's really asking, if you have a square that had area of 100, what would the side length be? Or, like it does ask here directly, what number times itself is 100? That's really what it's asking. Now, if you know this right off the top of your head, it's 10, of course. We'll show this in the tables as well. Yeah, the multiplication tables is nice because in this table, it's actually this diagonal right here that is a number multiplied by itself. Well, and you may ask, well, how do we know what number is multiplied by itself? You see how we just follow the row and the column right here? Like 36 would be 6 times itself. Or on this one down here, this 100 would be 10 times itself. Or up here, 4 would be 2 times itself. Okay, and again, if you have your multiplication tables down, it's just not going to take as long. If you need the multiplication table, just be careful because you won't be able to use that on the quiz, right? So on this first problem, it's saying, what number times itself is 16? So in this diagonal, I'd have to say, oh, there's my 16, if I could use a table. Otherwise, I'd have to ask myself, what number times itself is 16 again? Well, you can go through the first 12. We shouldn't see anything beyond the first 12, even though it looks like we will. Okay, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, boom. This reads the square root of 16 is 4. So on this next one, the square root of 49, again, what number times itself is 49? Hopefully you have that memorized, but here it is in the table, which means that we're looking at sevens on this one. Now you'll notice 169 is not in the table. It's not in the table. So, man, it's kind of hard to think about on this one. Yeah, what number times itself is 169? Well, it's not much bigger than 144, so we really shouldn't be like guessing and testing on this stuff. What I would do is I would just try 13 and then 14. And I know that is kind of guess and test, but it's inferential because it is, we're saying, well, it's close to the 144, which is 12 times 12. So I'd say, okay, 13 times 13, 3 times 3 is 9, 1 times 3 is 3. Now I'm in the tens place value. 1 times 3 is 3, 1 times 1 is 1, and we can see that's 169 right there. So that's 13 times 13 is 169, which means that the square root of 169 is 13. So there may be some work involved if it's beyond 12 times 12, right, which is 144. And yeah, I assume that you will see some numbers, maybe like 1 or 2 problems that go beyond 144 in the square roots. So sequencing. When we find missing values in sequences, you need to determine what operation is being used and how it is being used. Because if we look at this pattern right here, finding the next term in the sequence, it can be, well, I'd say that there's 2 different patterns that we may find in this one. In fact, all right, now we are dealing with multiplication and division, so it should be some relation to multiplication and division, even though I'm going to show you how it also relates to addition. Okay, like on this one, you'd say, oh, 16, 25, 36, 49, 64. It's all in the table, right? Which means that the next term should follow the same pattern. It's this diagonal here, so that next term here would be 81. All right? Now, that would be using the multiplication table, which is still multiplication. Well, yeah, I'll stop there for that one. But using addition on this one, you could say, well, 16 plus what is 25? And you'd find that you'd have to add 9 right there, right? Okay, well, 25 plus what is 36? And you say, oh, I know that's 11. Okay, well, 36 plus what is 49? That's 13. You see how there's kind of a pattern with these values that we're adding. So it's plus 9, and then 11, then 13. So what would you expect to add to this next one? Well, it'd just be the next 2 more than that. So that's plus 15 right there, right? To get 64. And 49 plus 15 is 16. So next you'd say, I know I'd have to take 64 and add 17. And sure enough, 64 plus 17 is 81. So we got to correct both ways, whether you use the diagonal or whether you used the addition pattern.